Good morning or good evening, depending which time zone we are. I'm Vadim Smilyansky, and I'm presenting a talk, Floquet calibration and error mitigation for large-scale quantum simulations on behalf of our Google Quantum AI team. In last 1.5 years, after our Beyond Classical experiment, there was a number of large-scale quantum simulations that were performed in our team. And they used some of the new calibration and error mitigation methods, which I would like to go over today and present some of the things that make the experiment work and some of the theoretical concepts that we showed was able actually to apply in experiment. So typically we consider there is a 3 general criteria for calibrating quantum circuits. First, that the circuits you actually try to calibrate should have the same structure as the circuit you intend to run for your application on experiment. Because the circuits that you calibrate to fine-tune the parameters require to capture temporal and spatial crosstalk between gates. So the structure needs to be very close. Second condition is that your calibration has to be faster than system drifts. And because quantum devices drift and fluctuate constantly. So you have to be faster than that. And third, that it needs to be very high accuracy if you want to have a really clean data for a large number of qubits and a large number of gates, because systematic errors can add quickly. And if you calibrate very well to systematic errors, even some of the noise properties are suppressed. There are typically 3 types of circuits that we considered so far. So one of them, for example, is a periodic quantum circuit, when you have a cycle of gates and you repeat it periodically. So example of that circuit with the new calibration, Floquet calibration tools, has been recently published in Nature. The first author is Charles O'Neill and co-workers that perform the experiments. Charles was talking earlier today. Then we have a type of circuits which is a random quantum circuit. And in a way, a random quantum circuit started from Beyond Classical experiment in October 2019, but more recent work on out-of-time order correlator was done by Xiaomi and co-workers. It's information scrambling and computational complex quantum circuits. And then there is a third type of circuits, which are structured quantum circuits, and mostly they were performed and investigated and put forward by quantum chemistry and quantum algorithm Ryan Babush team. An example, for example, is a Hartree-Fock simulation, which was published in Science in 2020. So one of the key elements of how we calibrate the circuits and individual gates is what we call Floquet calibration tomography. So let me describe you how that works. So suppose I have a gate, which is shown in blue. In fact, let's say it's a particle conserving, excitation conserving gate for 2-qubit gate. And I would like to calibrate it. It depends on a set of parameters. So swap angle, single qubit phases, control phase angle. So what I do, I create a periodic circuit where I add to this 2-qubit gate a single qubit gates with the phases Z1 and Z2. We call it auxiliary gate. And I repeat it n times. So the cycle unitary is characterized by the eigenstates of the cycle unitary Floquet eigenstates and by the eigenphases, omega q. Now the cycle unitary to the power n, which is the circuit unitary, right? It's characterized by the same eigenstates, and eigenphases are multiplied by the number of cycles. It's clear that the small changes in the parameters of the gate produce changes in the cycle unit, in a circuit unitary, which is multiplied by n number of cycles. So this is essentially amplified. And the small changes are being amplified, and therefore the angles could be estimated with the error proportional to 1 over n. So this gives rise to what we call Floquet calibration tomography. So what we do, because the goal is not to learn just eigenphases, the goal is to learn parameters. So this is what we do. We basically scan the output of that circuit, periodic circuit, for different values of the phase difference between single qubit gates. And then what we do, we record values of the eigenphases for different values of the difference between Z1 and Z2, which are single qubit gate phases. For example, here you can see that we plot them for different values of the swap angle. It typically takes a few values of the phase difference to actually learn the parameters of the gate. So that is analogous of the scan. I should say that that procedure can be done in a Heisenberg limited regime, and it was actually obtained in 2015 by Kimmel and coworkers. So that, in fact, you need only a logarithm of the precision of the number of different circuits in order to reach the precision epsilon, as shown here below. So what I wanted to say that here I want to zoom in on the part of the excitation conserving gate, 2-qubit gate, with the bases 1, 0, and 0, 1. What you can see, just to talk a little bit about the parameters. So theta is a swap angle. Now, what is it, zeta? If you set an excitation on 1 qubit and you don't jump after the gate is applied with probability cosinus theta square, but you acquire a phase zeta. Now, if you hop to a different side with the probability sinus theta square, you acquire a phase chi. So then there is a global phase. So we call zeta a local field, and we call chi a complex hopping. It's essentially a Peierls phase, if you want. Now, in order to characterize the performance of this periodic Floquet tomography, we compute a cross entropy between the model prediction that depends on parameters and the data. And that typically has a very complicated landscape, and we develop efficient algorithms, multi-grid algorithms, to find the global minimum that work fast. But the point is that the curvature of the local minimum describes you the variance of the parameter you estimate. And here I show an example of how standard deviation of a swap angle depends with the circuit depth. And initially it decreases, and the decrease of, here actually in this formula, I describe inverse variance. So inverse variance increases quadratically with the circuit depth, n. But then it's essentially begin to saturate because of the decoherence begin to play a role. So basically, if you look on a total standard deviation, it decreases linearly with the circuit depth, and then it saturates. And at saturation, we were able to reach the values routinely, something like 3 or 5 10 to the minus 6 of a radian, about 5 10 to the minus 6 of a radian. And I should say you that the time to reach that precision was enormously quick, because each cycle takes 35, 40 nanoseconds. And we have about 1,000 cycles to reach that. Now, I wanted to tell you that there were some challenges in how you perform that calibration, especially when the swap angle is very small. So the problem is that this Floquet calibration essentially introduces Arabi oscillations. And what happens is, if you have a zeta, which is my detuning essentially, I like to remind you what zeta is, right? It's a diagonal. So if zeta angle is not 0, then you have essentially off-axis rotation. Now, how I describe that off-axis rotation? For example, if I start from the state 0, 1, and then I measure the expectation value of the power z, you could see that it oscillates with the frequency omega, which is essentially a difference between the eigenphases, which is given here in terms of the zeta angle and theta angle. And zeta plays the role of the detuning. What is interesting, if I look in a Bloch sphere, and I show how the trajectory of this oscillation look like, starting from the state 0, 1, it's shown by this red orbit. The very interesting point here is the point which is shown with red dot. In this point, the derivative of the expectation value of z with respect to the parameter omega is 0. And it's really important. Why? Because the Fisher information, I would say the variance of parameter omega, is given by this formula, which is 1 minus z squared divided on a square of the derivative of expectation value. You could clearly see that at that red point, certain not desirable thing happens. Your derivative of z goes to 0, while the absolute value of z is less than 1. That means that your variance blows up. So that is actually shown here as a precision, as a function of the circuit depth. It undergoes this very deep oscillation when you basically lose the precision. Interesting that that negative effect could be mitigated if instead of starting with the suboptimal state, 0, 1, or 1, 0, you actually start with a state which points along, in a Bloch sphere, points along, say, positive y direction. Then the orbit will be given by this blue orbit, blue color. In fact, both red and blue are rotation around the axis, which lies in an xz plane at the angle rho to the z, which is given tangent of it given theta over zeta. So both are rotating around the same axis in xz plane. However, what is important that undesirable point, and now what I'm actually doing, I'm measuring the expectation value of y. So by that token, the variance is equal to this similar expression when z has to be replaced by y, except when the derivative dy over d omega equals 0, which is this blue point, y equal 1. So, or minus 1 in this case, absolute value square equal 1. So both numerator and denominator goes to 0, and therefore variance does not suffer. So you could see the optimal initial state and a measurement of y mitigate the precision collapse problem. And therefore, we can do it for a fairly small values of zeta and theta, which are very important, for example, on calibration, control z phase, control z gates, etc. So I'd like to tell you, I'm not going to go into all details here. I just very quickly would like to mention that there was a significant effort into the developing kind of benchmark for a Fermi Hubbard one-dimensional circuit, which is a two chains coupled to each other. It was pushed by Zhang and coworkers. And there was a very meticulous procedure that Zhang developed, which consists of a number of steps that essentially very much allows to cleaning the signal that correspond to the motion of the center of mass of a group of particles. And what I wanted to tell you that this procedure looks trivial, and it composed, because it just basically looks like experimental set of steps, but it does has quite a deep theoretical understanding and analysis here, especially steps like Floquet calibration and rescaling. And I would like to refer you to the paper by Zhang and coworkers from 2021 in here. What I wanted to do now is a little bit to switch gears. So we talk about periodic circuits. And of course, calibration of those gates were also used in a structured circuits like a quantum chemistry circuit, Hartree-Fock, then Ryan Babush team has published. But what I wanted to say is now let's talk about random circuits and what kind of error mitigation procedures we can develop here. So the random circuit of record, which was done in the fall of 2019, is a beyond classical, first ever beyond classical regime that was reached by our team, and the theoretical proposal by Serge Boise and coworkers in 2018, and the experiment was published in Nature in 2019. So the circuits typically have that structure. It's composed of layers. It's a 2D grid, and it's composed of layers. So each layer corresponds to the two-qubit gate, the same two-qubit gate, the Sycamore gate in that case, in that beyond classical experiment, which was applied in alternating layers or alternating patterns of qubit pairs. And then there is a single qubit sublayer in each layer. What happens in each single qubit sublayer? So for each qubit, we apply a one qubit gate randomly selected from a prescribed set of gates. And that set of gates also contain non-Clifford gates. So the circuit is non-Clifford. So, and then every time I have a new sublayer of a single qubit gates, for every qubit, I randomly select from the subset. Now, the outcome of that circuit in beyond classical experiments was just random bit strings. Now, if the goal is to actually understand the physics of what is happening in the circuit, then it will be, in particular, the circuits are manifesting the phenomenon of quantum chaos. It will be useful to actually look at the local observables. However, unfortunately, just in that random circuit, local observables are expectation values are exponentially close to their ergodic values, and correlations between them are exponentially suppressed. Perhaps the simplest experiment to measure the non-trivial local observables is the so-called out-of-time order correlator. So how this works? So suppose I have a circuit that apply the same circuit U, which I described before, or something like that, a random circuit. Now imagine that I just do some dumb thing. I just apply U dagger right after that. So the total is identity. And what I wanted to do, I don't want to get identity. So then I'm going to take one qubit right before I apply U dagger, and I'm going to apply what is going to call a butterfly operator, which meaning will be explained in a moment. So that butterfly operator could be, for example, a Z operator. As a result of this, the collapse, the cancellation is not perfect. And because of that, we have an effect of that not perfect cancellation spreading over the circuit. And in particularly, we can measure it on a side 1, for example. And the measurement of that on a side 1 would basically correspond to this average, which would correspond called out-of-time order correlator. What we measure in reality, we measure the following thing. Once the time goes by, the butterfly operator spreads. And at the time t, we would like to know the measure of how much that spread of the butterfly operator actually commutes with the measurement operator on a side 1. So that commutation is what or non-commutation of out-of-order correlator measures. Now, why this commutation or not commutation is important? Because obviously it takes time to spread the butterfly operator, to propagate all the way from the location of butterfly to the measurement. So if, for example, at the beginning, when the signal hasn't spread yet, then the out-of-order correlator actually equal to 1, because there is no commutation. The commutator is 0. Now, in a very long time scale, when the signal spread and more or less the signal become essential, the quantum state become full ergodic everywhere, then the out-of-order correlator is exponentially small. It's small in the dimension of a Hilbert space. So this is an experiment with 53 qubits. And the real part of the out-of-order correlator shown with this density plot. So it's between upper is 1 and it goes to the negative values. So the measurement operator is shown by black dot here. It's a Z operator. Now, what happens, different qubits are colored with a color that would correspond to out-of-order correlator corresponding to the butterfly placed in that particular qubit. So what happens, for example, with most of the qubits, the color is yellow. The out-of-order correlator is 1. Why? Because if, for example, it's cycle 1, right? So on a cycle 1, if I place my out-of-order, if my butterfly somewhere far away, then the signal from that butterfly in one cycle obviously would not have time to reach the measurement operator. However, if I place the butterfly operator right in the neighboring link, if I have a 2-qubit gate connecting them during that cycle, then clearly I have time to reach the measurement operator. That means that out-of-order correlator value at that blue qubit will be less than 1. I already begin to scramble information. Now, if I move forward to the 8 cycles of my circuit, then more and more positions of a butterfly operator would be able to generate the signal that reaches the measurement qubit, again in black. And those positions give OTOC values less than 1. They have a non-trivial oscillation pattern. Eventually, after long enough circuits, all of the positions on a qubit array would correspond, if I place there the butterfly operator, the signal would reach essentially the measurement operator. And in fact, by that time, if I wait long enough, then there is out-of-order correlator will be very small. I want to say to you that at intermediate time, there is a boundary between the out-of-order correlator less than 1 and the one that is equal to 1. It's a boundary between the areas where the signal has time to reach measurement qubit or doesn't. It's between this. That boundary we call a front. In general, a front propagates, filling the entire array, pretty much like forest fire. And very relevant for us here in California, unfortunately. And what is important that the shape of the front, the structure of the front, really depends on how the things works. So I wanted to tell you that there was a significant effort was done to actually do the error mitigation here, develop theory. I probably would not have time to talk about this right now, but I just wanted to say that we were able, through the very peculiar error mitigation techniques, which are cited in the literature, approach the beyond classical threshold in a regime where we need to improve our gate fidelity by a factor of 2, and at that point we will be able to pretty much perform the quantum experiment on out-of-order correlator, where it's going to take 1 day on a Summit supercomputer to do it. So the improvement fidelity on a factor 2 is not over challenging task. It could be done within a year or 2. So I would like to thank you, and I would like to invite our next presenter, Ryan Babush.